Hello everyone, January 29th. Well, I guess the most, I won't say exciting, but no, it's just the most, why I talked about the news, tech news these days is the new DeepSeek R1 model. Well, I have some reading material to do about this. Um, it's an interesting time that we're living in, that's all I can say, right? I do believe that um, I mean, it doesn't matter what is the truth behind this model or whatnot, but at least, and I appreciate it very much that it's open source, so people can really take a look. They have a paper out, so you can. So basically, you can do this if you want, if you have the means, but not an individual, but let's say a company can do it, and the real impact is it does lower the entrance barrier for this whole thing. Like they say, the moat around OpenAI is no longer there, or it's significantly lowered. And but I do think the other take on this, which is it would just commoditize it, democratize it, right? It's just gonna be more and more easily available. Now, however, I'm still not really using AI that much. I'm starting to use more uh, in my daily coding related to SQL, and it's just a faster way to check the documents. I think that's basically what it is. I'm using it this way. Like I have a very well-defined problem that I know some SQL syntax can resolve, but I do not want to go through the documentation to look it up. I just want an example, a syntax example, some explanation. So I just Gemini it, and Gemini is actually very very good. I mean, when I search on Google, search for, I think you guys see me do this. Really not very proficient with C++ syntax, and a lot of times I don't even know how to do simple stuff. So I just Google it, and then sometimes there will be a summary on the top, which is I think Gemini, right? Give you a summary of how to resolve this problem. It's like it saves you the effort to click each link and then read through whatever is in there. It's a very I'm starting to use it more, and I still don't use it for code generation. For one reason, I'm just too lazy to set up in the Vim. I mean, even in my work environment, I can use it, and I think I have it on. It's still a debate at the moment. It does make a lot of things easier. I would say generate documentation is much easier, much easier. You basically just tap it through, right? But writing code wise, I sometimes I feel annoying. Really, sometimes I really feel annoying. Like I want a feature that I can turn on, or it will automatically help. It will like the AI will help me write documentation, but don't help me write the code itself. Because it just I want to write. I want to type the code myself. I don't want to just every time just tap, because like tap it through, you have to read it again, and things are wrong, you have to change. And it just messed me up. I don't really like it. But documentation wise, dude, this is a game changer. Documentation is absolutely a game changer. All right, anyway, we have a tough question today. A solved one. Divide nodes into maximum number of groups. You are given positive integer n representing the number of nodes in an undirected graph. The nodes are labeled from 1 to n. You're also given a 2D integer right edges, where edges indicate that there is a bidirectional edge between A and B. Notice that the graph may be disconnected. Divide the nodes of the graph into m groups, such that each node in the graph belongs to exactly one group. For every pair of nodes in the graph that are connected by an edge, if A belongs to the group with index I and B belongs to the group with index Y, then Y minus X must equal to 1. Return the max number of groups into which you can divide the nodes. -1 if it is impossible to group the nodes with a given condition. So the first one, it says the graph may be disconnected, right? And we need to divide them into, so basically the requirement is just if two nodes are connected, then they must be put into adjacent groups. I have no recollection of this one at all, like at all. Apparently I have solved it before, but I don't remember this at all. Every pair of nodes in the graph, we want them to be adjacent group. Basically, that's what it is, right? I want them to be adjacent groups. And divide the nodes into m groups. So the nodes can be divided into groups. So basically, if two nodes are connected, they cannot be in the same group, right? They have to be adjacent groups. Huh. And if you have a disconnected, right, if you have a disconnected, like two disconnected graph, then they can be in two different, right, they can be in two different groups. It's just each pair, right? Each pair has this requirement. So if I have only one, yeah, let's run some examples. These type of problems usually require some example to start with. So let's say we have a requirement, and yeah, we have one. All right. I just say one. Why are you typing two? Edges length. We have to have an edge. There is at most one edge between any pair. Okay. And can we point into itself? Not sure. Just give it a shot. Oh, there is a requirement. Oh, okay, they cannot be the same. Ah, that's fine. So it's not possible to have one node, right? If I have no, so at least we have to have two nodes. So if I have two nodes, and I must have, so, okay, so we can have four, let's say 1, 2, 3, 4. All right, that's the smallest disconnect, right? Because we cannot have a group with just one. Because you have to have an edge. Oh, we have to have an edge. Oh, we can do this. All right, like this. So 1 and 2, and then 3 is by itself. So we're talking about 1, 2, and 3 by itself. Is it test case 4? Oh, that was a mistake. All right, so the answer is 3 because we can have 1, 2, 3. Okay, that makes sense. All right, so what do you think? Well, apparently you can do DFS. No, BFS, right? This is just like layers, 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 and layers. But you also have this like a cycle. Huh. All right, let's see what this one is. So we have 1, 2, 2, 3, and a 1, 3. You see, in this case, it's not possible. So every pair of nodes in the graph, right? Then they have to be, so each pair has to be in a different group. So this has to be in a group, this has to be in a group, right? So 3 has to be in a different group as 2. And 3 has to be in a different group as 1. But why, if we add node 1 to the first group, node 2 to the, and node 3 to the third group to satisfy the first 2 edges, you can see the third edge will not be satisfied. Okay, the third edge will not be satisfied. Oh, because you're labeling it. This is edge. This first is 2 and this is 3. But then the 3 has to be adjacent. Okay. So the nodes that are connected must be living in different groups, right? So let's use this example. 5, 1, 2, 3, 6, 4. So nodes that are I'm kind of thinking about topological sort, which we can see this has to be in by itself, and this has to be in by itself, right? But we don't know what indices they should be. And then so 1 has to be, so 1 has, so 5 is this, right? So if I remove it, then we have a cycle. So if you have a cycle, each one has to be in its own group, right? If you have a cycle, each one has to be in its own group. That is not true. That is not true because so like this has to be in its group, right? So 4 has to be in its group, 6 has to be in its group, 2 has to be in its group, but 2 and 4 can be grouped together because they do not have a link. So basically if we have a cycle, right, then if you set one of them as a group, then this can all be in a group. Oh, but then this cannot be in a group. Because if you say this, and then this, then these has to have the same number, but they cannot be together. Right? So this is not allowed. Maybe there's a mathematical thing here. For example, if it's even number in the cycle, that will be always possible. Alright. I choose 1 as the first group, and then this can also be the second group. This one can also be the third group, and this will be the fourth group. Right? So we say if n mod 2 is equal to 0, then we say we'll get n minus 2 divided by 2 plus 2. So it's just n minus 2 plus 1. right? And in this case, we have 4. So 4 divided by 2 is 2. 2 plus 1 is 3. So we can have 3 out of it. Right? So we get 1, 2, and 3. But then we also have these two. Oh. Yeah. Huh. Like if you choose this, then it doesn't work. But you choose the other way, it works. So if it's odd, right? If it's odd, then if you pick 2, 2, 2, eventually you'll pick 2 like this, which is not allowed. So you cannot pick like that. But that's the only way for you to pick. There's no other way. So yeah, so like if we have a cycle with n is odd, then it's not possible, right? That's not possible. There's no way. Because regardless, you will have to handle the cycle, right? You will have to handle the cycle, right? One way or another, you have to handle the cycle. Everybody in the cycle has to be in groups, right? So a question becomes, if I find cycles, then I count the number of cycle, right? And if the number is even, then I know how many groups it needs to be having. But in this question, you can also have the other way. Like, what if I start going like 4 by itself, 1 and 6 by itself, and 2 by itself, right? And then 5 has to be by itself, and then 3 has to be by itself because connected to here. So 1, 2, 3, 4, 5. Why is that not right? Oh, it's because if you mark it 1, 2, 3, so anybody connects to 1 must be either 1 or 3. Right? So we have 3 and 1. So 5 connects to 1. So 5, this has either be 1. So this either be the same group as 2, which is good, which is okay, or it has to be the same group as this. Right, so this is the same. So now for 2 is a 1, 2. So this will either be a 2, which will merge with this, which you can, because they're not on the same level, so you can. So now in this case, we only have 3 groups. It's actually worse than this. All right, so we haven't solved anything yet. All we find out is if you have a cycle, you know that this will do 4 groups, right? Because 6 divided by 2 plus 1 is 4. You know, just have 4 groups for that. You know it, right? But then these might have something sticking out, right? And then the something sticking out might also have like another cycle, right? It might have another cycle. And how do we handle all this? I guess it depends on, so we have a node, right? A node can have a lot of different ways leading out to other nodes. Now we know that this node has to belong to a group. We don't know what it is. Let's say we say this group K. Then we know all the other ones has to be either K plus 1 or K minus 1, right? Either K plus 1, and then we need to see if there is any connection. If there is a connection, then it's not possible. But if there's no direct connection, we just have one node, and then we just shoot out all the other nodes. Now we know some of it can be K, some of it can be K plus 1, some of it can be K minus 1, right? And from there, no idea so far. Drawing blank. Oh. We can say to maximize it, we try not to merge with the previous one. Then for a node, if it has an edge already, right, then we have a group, so the next one must all have the same group, and then everybody next must have the same group. Is that the optimal way to do this? I'm not sure. I want to try one more time. If I say I just chose this to be a 1, is it connected? So this must be 2, because I only have 1 connected, right? So this must be 2. Now technically we can anything, right? Anything can be added to this group, but anything connected to this because we're going down, we don't go back. So this must be 3. This must be 3, right? And this is connected, so this must be 4. Right, this must be 4. Is that? Yes. All right, so where are we? We're trying to see if we can iterate through this thing. Yeah, I would say this, because these are connected, so they have to be 3. This is connected. The next one has to be 4, and then this one has to be 4. And then we just see if these can group together, and the answer is yes, so this one will give us 4. Right? And now we know from here, so 5, 1, 2, 4, 3, 6. We say if this is 1, this connected, it must be 2. These connected, this must be 3. And this is connected to this, so this must be 4. And this must also be 4. So now we're going to check these can be 4. Yes. Okay, let's try another way. Maybe we can do it differently. You know, no, that's fine. Let's say we start from 1. We say this is 1. Everything connected has to be 2. Then we need to check pairwise. Do they have any connections? Oh, pairwise. Pairwise. That can cost some time. Cycle. And this is the third one. I'm thinking. 1, 6, 3, and then 1 has 5. One also has a 4, and these also connected. So if I did this way, BFS. This is 1. This is 2. And this is 3. How do you know this is a 2? Because I start from a node. It can have, so I start from a node. I can have however many. So I say this is a 1. Then when I go down the second level, all of them will be grouped as 2. All of them, right? Then on this level, I have all that, and then we're gonna go to the next level. So when I go to the next level, of any of these, they have a children, right? Pointing to the same group. So we'll have visited. So we have visited. These are visited in the previous level, because I want to know if there is anything in this. So what I'm trying to say is, if I have a set of this level, right? We have a set of, so we have a level set, and as I go right to a node, we'll check if it's visited, right? And at the same time, I also need to check if it's in the level set. If it is in the level set, then it's impossible. So we don't consider this situation again. So now we'll swap to the next one. We'll start from the next one. So each time, yeah, we go through this, and then we have a bunch of nodes. If they do not have inner links, then we're all good. So we have this level. Then we go to the next level, right? So all of these have things coming out, right? So we have next up. So we'll get all these out, right? And then these will become visited. And for the next level, right? For the next level, I do the same, right? I only consider like it's visited or the current level. So as long as it's possible, then we can have this level. So we just brute force, right? We start from every single node. We start from every single node. We do BFS, and just see if we can go through. And then we just count the number of levels. And we want to find the deepest level, right? And since it's 500, let's see if it works. If it doesn't work, then we're gonna call it. I don't have time today. It's like, when do you even have time? You never have time. Jeez. All right. Factor of Boolean visited and false. All right. And do you need a graph? I do need a graph. So we say n of 4 outer edge of edges. We say graph edge 0 dot pushback edge 1, and we basically do the same thing. 1 0, right? So we have these two things. So we get the graph, we get the visited, and then we need a queue. Actually, I don't want to do it a queue. I do not want to do it as a queue. I want to do it as a so essentially we'll get the current level. We use it as a vector. Okay? We use that as a vector. and we just create a new vectors. Vector, why don't you just directly use a set? That is a good question, right? Okay, hold a second. Let's say we have BFS, right? So we have the start, and we'll do the graph, and I forgot, clear vector. Oh. The memory allocated to the vector is not released, so I should not do clear. I remember it still has the memory space. I think it just the pointer points to back. Okay, this is not what we want. I think it'll be easier we just create it every single time. Right, so essentially I have a res equal to -1. Okay, and we'll say for int I equal to, I see, that's -1. Right, so we say I equal to 0 and I plus plus, and we'll get the visited. We'll recreate every single time. Don't care. Right, and we are going to say, oh, why you do it here? Ah, you do it here. Dude, man. You do it here. Int n. Yeah, you do it here. So we just call res equals to maximum res and BFS I and graph. That's it. Right, we will do a BFS in here, and once we're done, we just update its value, and then we say return res. Something like that. Okay, so now we are going to really run the DFS. So here's what I say. I'll do a set, right? We can say set of int q. Okay, q dot insert start, right? And then visited start equal to true. And say while q dot empty. We can say a new set of temp. Get a new set, and then for all int node of q. I can do that, right? For int node of q. We also have levels. 0, okay? And then not empty, level plus plus, right? Because this way we add, we are at the current level. And for each node, right? Then what we say is, yeah, if it's go above, ooh, that is interesting. I think if it goes to anything that you have visited, that is going to be bad. Hold a second. So what if I have, let's say this going all the way back? Let's say we have a 4 linked to 2. If I have a 4 linked to 2, oh, then it will be discovered in here. then it will be, oh yeah, that's fine. All right, so for each node, I'll go through, right? For each node, I'll go through, make sure if it's in the queue, then it's a bad, right? If it's in the queue, that is bad. Yeah, so we say for current, okay, we can say, and call it current, and we can say next in graph current if queue dot contains next, return -1, right? There are links within the current the current layers. One of the current layers node is linked to another node in the current layer, which is not allowed, right? Because we're doing the current node, we're looking at its next, right? And if its next is in the same layer, then that's bad. So if not, then we'll also say if next is not visited, is if not visited before, visit next so we start with, yeah, I really don't think we should do it here. Right, we don't do it here. So Q put start. Okay. Now go through everyone. Once we go through everyone, we'll visit it. This is when we visited, right? We visit is true, and then we go through its next, and if its next is, you know what? No, 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 and no. I put it here, I put it outside, and then I go through this, right? So the current one is always visited, it's already visited, okay? Then we go to the next one, right? And then for the next one, I will get, if the next one is in the queue, in the same queue, that's bad. If the next one is not being visited, here's the thing, visited next will equal to true, right? The next visited will be true, and we are going to put this next in this, right? We'll put the next node inside. That's the next layer, right? So we go blah blah blah, we go through every single one. Once we're done, we'll say q will equal to temp, right? Q will equal to temp, and then we go back on. So we try it again. So once it's all done, we're in the final level. So we start with this first level with plus plus, and go to the next level, right? Plus plus, and we go to the next level. Then we plus plus. I think we just return level. All right. Let's check if this one satisfies. All right, we have a few test cases. I run through it. The last one is not right. Ooh, that is correct. That is correct because I have a disconnected. Holy crap. Ugh, disconnected. So res, ugh. Res is this, and running max, current max. All right. If not visited, if not ooh, shoot. How do you know if it's been visited or not? Damn. I do need visited. Overall visited. Ooh. So, oh my goodness. So what I need is a vector boolean of overall visited. Right? All right. Overall visited. Start. That's true. Something's not right. But anyway, overall visit is true. Then overall visited, make it true. Okay. So now we say if overall visited I. So if I has not been visited overall, right, then we say current max equal to BFS I and graph overall visited. Else, holy crap, that ain't right, because it might go to the next one. Holy moly, I need to know which group it belongs to. Oof. All right, it's not overall visited, it's the graph, the connected index, the connected parts, the index of the connected. So if it's the same, then we'll do that. Oof. All right. Hold on. So, oh my goodness. All right. So basically, all right. It's not overall visit. It's the index, right? The component index mapping. right? It's component index mapping and components. Okay, we have components. And then we say if component index map comps I is smaller than 0, which means this one has not been done yet. So we are going to say comps dot pushback 0. Right, we're gonna push back 0 and that's your index, right? So we're gonna do comp index map and comps dot size -1. Yes, this is the index. So basically we'll set everybody to the same index, right? We'll set everybody to the same index, and actually no, we can say current, let's call it current. Hold on. So we say current is this, and then comps dot pushback current, and this is actually gonna +1. No, it's just by itself. Okay, so let's change this. So this is not overall visited. This is gonna call comp index map, and we're gonna say index comp component index. Alright, so basically we are gonna change, so all the overall, this is gonna be comp index map, right? And then the start, this is gonna be comp index, right? And here is also gonna change, this is gonna be comp index. It doesn't matter, eventually we'll get out the current number of levels, and then this is the current number of levels based on this, and I'm gonna push this in because I have never done before. This is basically a fresh, right? Else, that means the current node has already been in a index. So what we're gonna do is we will do, oh, that's fine. We'll do BFS I and graph comp index map comp index map I, right? So we already done it, so it's fine. We just go through this one more time. Comp index doesn't really mean anything. We just get a new way, right? We have a new way of BFS it, and when it's done, we say comps so int ci shall equal to, oh, that's had easier, comp index map I, right? This is telling me what component index it is, right? What component index that we have already done. So now we can say ci shall equal to std max comps ci with the current. And I'm pretty sure we will all like to see one less variables. So here's what we're gonna do, right? We're going to say the pushback. So this is just the node I has never been visited before. we will start BFS, right, with BFS with I as the root, and store the layers, right? Store the layers. And store the number of levels we can get. In the as a new element in the comps array, right? So here is node I has been visited before, and we know which component it belongs to, right? We will run the BFS again, but instead of creating a new component, we update the the level, right? Update the level of the same component as before, same component that has already been created, and keep the larger value, right? So basically this is what it is, and I'm pretty sure you will see it. You'll be very happy to know that we can do away with this one as well. Okay, so there's this. Now once we're done, what we're gonna do is we say int res equal to 0. I need to go through. If everybody, right, then we just say for int c of comps, right, res plus equal to c, and we say res if it's equal to minus comps dot size, which means everybody is -1, right? Then we return -1, otherwise we return res. Okay, so this is kind of a new idea. Save this. Alright, we're gonna run through. Hopefully we will be able to handle the edge case. Yeah, looks alright. 2493. Brute force. We start from each node and run BFS to see how many levels we can get. While doing the BFS, we check whether there is any link between the nodes of the same level, right? If there is, then BFS fails, and we cannot produce a group out of this. Otherwise, we can return the number of levels. Since the graph can be disconnected, we need to do the BFS thing for each separate graph, and the final answer is the sum of the max BFS levels from each disconnected components. I'll call O(n) squared. Not very sure, but we'll see. I'll run it one more time, and let's see if it passes. Huh. Oh, okay, I see. As long as anything is a -1, yeah, so you're right, because the components, so if, yep, I think I understood it wrong. It's not everybody, it's as long as one of them, right? So if C is smaller than 0, return -1. Otherwise, rest plus equal to C, and we'll return rest. So, all right, that's a little oversight on this, but try it again. Look pretty solid. We already passed a lot of test cases, so I'm pretty sure this one will pass. Brute force. Yep. Now, is it good performance? Of course not. But it's a hard problem. I'll take it. I'll take it. All right, 1724. Submission length exceeds. Wait, what? Exceeds limit. I have no idea what that means, but I'll take it. I don't know what this one means. It means you need to pay. That's what it means. 1724 is very bad. Very bad. I wonder maybe if I submit again, it won't pass. Well, but hey, it works. It works. I'm going to say let's throw it with everybody else, but no, I still have some capacity, just a little bit. Let's read. Graph coloring, longest, shortest path. Holy shit. Then it's definitely not O(n) squared. I feel like it's O(n) squared. Isn't this not O(n) squared? Right, we go through every single one, and then each one will have to go through n. I feel it is O(n) squared, but what's m? M is the size of the edges array. Ah, that's not O(m) squared. It's O(n) times n plus m. It's the same. It is the same. BFS and union find. Oh, I think this will very much look like what I did. All right, so I'm not 100% sure, but I feel this solution will use union find to find the different, this one, right? You'll use union find to find different components, and for each component, you're just gonna do this. What I'm not sure is, I don't know. I don't feel like reading anymore. Man, you're just gonna keep accumulating this. You gotta deal with this. I don't know. I mean, do you think it can be optimized? do you think you can get more out of it? I literally have no idea. No clue. I mean, I feel like some may not require. I don't know, honestly. No idea. Maybe we can say, can we say it is always better to start from a node that has no integer? Something like that. It's hard. Man, it's hard to say it that way. I don't know. I'm sticking with this. Maybe I have a previous submission. I do have a previous submission, which is also pretty bad. Dear me, what the hell is this? Oh man, I think this is a... Oh, did I do this myself? Alright, so this is the union find. And union find. This is the graph. Default dict. This is to find each component. And once I get each component, we get this, and we do the maximum. If it's not possible, yes, that's almost exactly the same, but union find, I see. But this should be the same performance as this. This should be the same. And of course, visited, right? Visited is a set. You have to go through them every single time. And here you are doing the same thing, but we use the queue, right? We use the queue to be a set. I think this is about the same as union find, but this blue, this code coloring, this is interesting. All right, we'll have to read it sometime else. I don't have bandwidth. Man, we need to do this. We need to read about this. I'm already forgetting what this one is. All right, I already forget what this one. I didn't read the tutorial. I had to do this. All right, I think these we can just close down. I don't ever think I'll do this again. No way. No, I don't think I'll do this again. I think I'll leave one of them. Ooh, this is binary lifting, right? Oh no, this is not binary lifting. This is do it 2 rounds. To find the height of after node is removed. I'm gonna close it. I remember one of them I did not solve this, but it's very hard. Shortest padding room. Oh. Oh, I remember this one. Absolutely. Oh yeah, it is a copy paste. This one's copy paste. Yo, you have to. Yo, man, you have to go back to this one. I didn't solve this one. This palindrome, I must solve this myself, or maybe? Oh, really? You did that? Jeez, man. Oh, it's just a hard problem. I don't recall at all. What else did I do? This is also that's a worse solution. How about this one? Yeah, I think this is a very hard one. I don't recall at all. Ooh. Count of integers. So many, man. Lowest ancestry. Yeah, we have to give up. So, like sometimes you're thinking, yeah, I'll go back for it. I'll go back. This is binary lifting. Yeah, I think this is binary lifting. Nah, no way. This must be the one that I use of extremely convoluted way. Okay, so some of them I want to keep. Some not so much. Dude, that's it? Alright, we just like these has to keep. This one, yeah, we'll close this one. I remember this one I want to investigate as well. You want to investigate everything. Oh. Oh, I remember what this one is. Oh, minimum reverse operation. They are all hard problems, man. They're all hard problems. Yeah, shoot. Binary lifting. Oh, it's the same ancestor, right? Kth ancestor of V. Oh. Yeah, lowest common ancestor. Oh, there's a target. Lowest common ancestor. I'm not gonna go through those for sure. If every encounter problem requires it, I will just go look for the solution. It's just so much things to learn, man. At a certain point, you just like, yeah, enough is enough. I'll see you guys tomorrow.